Last time we discussed computing the Fibonacci sequence using various methods. We had a recursive strategy, and then we tried this dynamic programming solution. It turns out that dynamic programming is a special type of algorithmic strategy, and there's a related strategy called divide and conquer. Divide and conquer approach to solving problems you can apply when you can take your big problem, break it up into some non-overlapping subproblems, recursively solve the subproblems, and then combine the results. We're going to see an example of this in MergeSort. So let's just discuss more details of how we apply divide and conquer, and we're going to see several examples in the next couple of lectures.
Let's now talk about divide and conquer algorithms. A divide and conquer strategy is, roughly speaking, an approach to solving a problem where you take the problem, break it into non-overlapping, smaller subproblems, recursively solve the subproblems, and then somehow put the solutions together. Let's consider the task of sorting a list of n numbers using MergeSort. So here is an example. So the input is a list of n numbers. Let's assume that n is a power of 2 for simplicity. The output is going to be a sorted version of the list A. We're going to break A into two sublists, A0 to n over 2, the first half of the elements, and then A n over 2 to n, the second half of the elements. We're then going to sort each sublist, and then we're going to merge these two sorted sublists into a single sorted list. Let's now write some pseudocode to describe MergeSort. I'm going to use my favorite pseudocode known as Python. Okay. So the first thing that we do is we check the length of the list. If it's only 1, then obviously a list of length 1 is already sorted, and since you can just return that list. So this is the base case. Now we take the list A, we break it into B and C, which is the first half of the list and the second half of the list. Now we recursively apply the merge sort on the list B and C to get lists D and E, which are the sorted first half of the list A, and E is the sorted second half of the list of A. Finally, we apply what's called the merge operation, which will take the lists D and E, each of which are individually sorted, but we'll combine them into a fully sorted list F. We'll have to describe what this merge operation is exactly.
Finally, we return F, the sorted version of A.
The word of the day today is chimpanzee. Is this a chimpanzee? I don't know, because my dog chewed off the arms. But the word of the day is chimpanzee.
To understand the running time of MergeSort and also to see how the merge operation can work in practice, I'm going to show you this on an actual example. You can look at the book for the precise code of how to design a merge operation, but I'm just going to give you the visual demonstration of what's going on. So let's say that you have an array A. So here is your array A with 8 numbers. We're going to try to sort this array. Here we've broken the array A into 2 subarrays of half the size. Now we've taken these 2 smaller arrays and we've individually sorted each one of them to get D and E. This is precisely the divide and conquer strategy. As you can see in practice, we took an array A, we broke it into 2 smaller arrays, 2 smaller subproblems. We then solved the subproblems recursively by using the merge sort algorithm on these smaller arrays, and now we're going to have to combine these into one big array. That's the sorted version of A. Now to see how we're going to get the final output array F, which is the sorted version of A, what we need to do is maintain 2 pointers, one initially at the beginning of list D and the other at the beginning of list E. We take a look at these 2 elements where the pointers are pointing to, and we notice that 0 is smaller than 2. Then we put 0 in the first element of the array, and because we've now taken away 0, we now move the pointer over to 4. Again, we look at whether 4 is larger than 2. We notice that 2 is the smaller, so we take 2 here, and we move the pointer on this list over by 1. Again, we compare 3 and 4. We notice that 3 is smaller than 4. Therefore, we put 3 in the box. We take this pointer, move it over here, and so on. At the end of this process, we may have some remaining elements in the list. For example, here we have 7 and 9. We're going to put the 7 in. We've now run out of, we can't move the pointer over any further. So we take whatever's left in this list, which is actually just 9, and we just stick it onto the end of this array. And now we have a sorted version of A. So let's think about the running time of this algorithm. Okay, so initially we had to do an operation by splitting the array A into 2 subarrays. This might take, well, it depends on what kind of data structure you use, but let's just say that this takes, in the worst case, this takes O of n time to take an array and to copy it over into 2 new arrays, right? You have n elements initially, and you have to copy into 2 sublists of smaller lists of size n over 2. We then had to apply merge sort next. So how many operations did applying merge sort on 2 smaller arrays? Well, we had to do something twice, and the running time, T of n, right? We're computing T of n. T of n is the running time. And this took 2 operations of size n over 2 because these lists are half the size. So they had to do 2 times T of n over 2 to apply the merge sort on these smaller arrays. And then how much did this last operation take? The last operation took on the order of n steps. Why is that? If you think about what I did there, every time that I inserted a new element into F, I had to do a constant number of operations. I had to compare 2 numbers. I then had to move a pointer over and then go to the next step. But in total, that's a constant number of operations for every iteration. There are n iterations, therefore it took on the order of n time to complete. So the total running time is T of n equals 2 times T of n over 2 plus O of n. That's the running time. Now looking at this, it's not clear what this is going to end up meaning. What this is going to mean, we have a recursive expression for T of n. It doesn't actually tell us exactly what the value of T of n is, but it turns out we're going to learn soon that this is roughly O of n log n. In fact, it's actually going to equal n log n, so let's write equal to. And we'll see why that is in a future lecture.